Hello everybody, my name is Jakub, I am CTO of SkyEngine, and today I'm going to tell you a few words about ray tracing for deep learning. You all know that at the moment, data acquisition and manual labeling are the most expensive and time-consuming parts of almost every deep learning computer vision projects. Moreover, dataset obtained classical way are very often unbalanced, and manual labeling can introduce lots of errors. So a couple years ago, we asked ourselves a question: do we really need to have a real data to try deep neural network models? Maybe instead of going to a street with camera and doing manual data acquisition, we could recreate the problem in virtual reality and try AI algorithms in virtual reality. We started our journey from gaming engines and rendering systems dedicated for VFX industry, but it was almost impossible to achieve a good accuracy. These solutions were not efficient enough for our purposes. We had to do lots of hacks, and very often model trained on synthetic data from, let's say, a gaming engine was able to work correctly only on other synthetic data from the same gaming engine, not in a real world. And that was the reason why we decided to start working on our own rendering system, which is dedicated and designed for deep learning. SkyEngine is an evolutionary AI platform being able to do a rendering of predefined scene in a feedback loop with training of AI model. In fact, SkyEngine can auto-balance a dataset by a detection of scene parameters like some position of lights, objects, reflections, maybe some properties of materials, which makes images being ambiguous for a model being trained. So at later stages of training, SkyEngine can change distribution of such parameters to focus only on the most confusing for a model situations. Okay, but let's look at a couple of examples of how SkyEngine could enable us to solve a couple of problems, data science, computer vision problems. So one of the first pilot we did was a pilot with New Zealand Rugby Union. You probably know that there is lots of models, statistical models of game, which enables the coach to choose a correct strategy for a game by an analysis of strategy of opponents. And there is also lots of software on the market dedicated for this purpose, but still the entry point for this software is a manual analysis made by a huge group of students who drag and drop players into virtual rugby stadium and manually adding labels to players. So the question here for this pilot was, could we automatize that process? Can we do automatic analysis of a game, extract players, compute the position of players on a stadium, and recognize some actions of players? So actually the problem is pretty complicated also because we are aiming to use broadcast cameras, so dynamic cameras with where the focal length changes as well as a position of camera. Plus, we could have motion blur and lots of other artifacts like compression artifacts. So you can imagine that doing this project conventional way, we would need to have lots of data from manual recording, lots of previous games. We would also need to do manual labeling, and if we want to have a 3D position of players, then we need to have access to GPS data from GPS systems. So probably we need to have a contract with one or a couple of rugby teams and access that data. So pretty complicated stuff. But in our case, how we could approach the problem, instead of doing a manual labeling and manual data acquisition, SkyEngine could create a virtual model of a stadium, could place their group of players with attached motion capture data, could simulate the artifacts like motion blur, change the crowd, change the lighting parameters of or other parameters of the footage. Also, because we created this synthetic virtual environment, we know exactly what is where, so we had a very precise labels. We could also generate super precise semantic masks for tasks like semantic segmentation. And also we could do something more, so we had access to full 3D data, so we could, for instance, highlight the most important parts of body of a players, which will be useful to recognize some actions like kicks or passes. And we could also use a precise 3D information of body position, but also about internal configuration of body of a player. So we could train a model for super precise pose estimation. What is also interesting about this project is that we managed to complete it within a couple of weeks, I think 3, 4 weeks, to achieve good results. So, in a comparison to standard workflow with data labeling, acquisition, unbalanced data sets, data augmentation, and it could take ages. And so we just had one data scientist and one CG engineer assigned to that project, and we achieved pretty good results. So, the video which you can see on that slide is just a random YouTube video with a rugby game. But you can see here the model trained over one night probably on synthetic data sets generated by Sky Engine, and the model is able to recognize players, to estimate position of player in 3D, to compute distance or velocity, or also to recognize the action which player is doing, like kicks and passes. So this was a nice example. This was sport analytic example, but actually we work in a couple of industries. So we have also projects related to healthcare. We have a very good capabilities to simulate materials, also tissues. We have projects in sport analytics, which I already presented, in manufacturing and robotics, and also in agriculture. So another interesting example about how easy it is to use 3D synthetic data is a project this time from autonomic inspection in telco space. So what you can see here is a model of a device of 3G device with some cables, and the task was to do autonomic inspection by a drones to check if everything is connected correctly. So in that case, again, there is no data set dedicated for this purpose, and data acquisition would be very time consuming because you need to have an army of people with drones um, doing data acquisition. Also, once we have data acquisition done, there's another problem because in next month another set of devices can be released, and we are coming back to the same problem, lack of data. But usually the manufacturers of such devices have a CAD models of the devices. Also, it's a pretty simple geometry to create. Instead of using real data, again, in that case, SkyEngine could generate just precise simulation of such devices, also with semantic masks, if you like to check connections, let's say. So we can simulate various weather condition, various lighting condition, and generate semantic mask in the same time and solve that problem. So it's pretty cool. Just to conclude what we just have seen, SkyEngine as a technology enabled us to do a synthetic 3D data generation, which saves lots of our time and money for data acquisition, and also improve accuracy of our models by removing human-based errors in a data set, by auto-balancing a data set, and also by the possibility of a generation of additional information like 3D information, which we could use for our models during a training. But what exactly we have in SkyEngine? So in the heart of our system, there is a GPU-based ray tracing engine, which is built on top of Nvidia optics library, super efficient one. We also have a set of tools which are dedicated for domain adaptation, style transfer to guide rendering process. So we can make sure that the model trained and synthetic data is ready for inference later in real world data. We already have also implemented the garden of neural networks. So for training of models operating in 3D space, time space, and models dedicated for various of other things. Also, we have a multi-GPU and network level scheduler, so the system is able to do a rendering in distributed way. And we are also tightly integrated on a level of GPU memory with PyTorch, and now we're also working on integration with TensorFlow. So we can look closer to these things. So one thing is that we are aware about the topology of more complex systems dedicated for deep learning. So, for instance, Skyeng is ready to run also on DGX2 machines, on Power 8 and Power 9 machine. We can figure out the topology of PCIe switches or NVLinks, and we can correctly distribute the rendering part and the training. So a couple of GPU can do a rendering and swap data with other GPUs responsible for training. Um, we have our ray tracing engine implemented with good physics of rays. So we have implemented physics of visual light, but also this is a multispectral rendering, so we can easily add the functionality of infrared simulation, or even we use Skyeng for X-ray simulation to compute transmission for some materials. What is also important to highlight here is that we are compatible with existing software for 3D, so it's super easy to export the scene from Blender or Maya and import it to Skyeng. We have support for various of animations format like Sony Pictures Alembic format. But the most important for us in a process of creation of this rendering system is to make it the data scientist friendly. We also have implemented materials like we are compatible with Nvidia material definition language. So you can see here a nice quality render of some carbon material defined in NVIDIA material definition language. This is our shader ball. You can see all reflections and everything computed correctly. So in many cases in deep learning, we do not need to have a photorealistic quality, but if it's needed, we can deliver that. Also, we have lots of GAN-based modules implemented. This is actually hidden magic in our system, so we can learn the feature space from small sample of real data and use it to post-process the rendering, or use it even during a rendering. And so in that case, what you can see on these pictures, we really like this picture. This is an extreme example of style transfer in Skyeng. So on the left side, you can see just the geometry of pylorus. This is a valve in the bottom of a stomach. This is from our one of our endoscopy-related projects. But on the right side, you can see how the system simulated the tissue. So the system learned from a real data how usually the light behaves on a surface of tissue. And we just use our own style transfer modules to post-process left image and to achieve the right image. So right image quality is not perfect because this is a capsule endoscopy, so this was a low resolution camera. But still, you can see how the system was able to learn the general look, the generalization of tissue. Usually, in such cases, we do not use such extreme support, some extreme approach. We usually we usually prepare the textures at the beginning together with geometry, and use these GAN models just to do a final domain adaptation. But in that case, that case shows very well our capabilities. With Skyeng, user receives lots of models already implemented, ready for distributed training, together with render data sources to speed up the configuration of rendering process. It's worth to mention that we also provide models like capsule networks. So CapsNet works pretty well in our case when we can provide data of 3D objects captured under many different angles. So we can build into capsule networks the general shape of the object. Also, we've got lots of autoencoders implemented and lots of GAN models, so everything what might be needed in this kind of projects. We are integrated on the GPU memory level with at the moment with PyTorch, but also we have work in progress with TensorFlow. So actually, in many cases, for research, let's say there is no need to have to process training, like a data generation first and rendering slide later. We can generate data on a GPU directly to a memory, which is next being to which is next going to be consumed by PyTorch. So we can share a memory between our rendering buffers and PyTorch buffers. And what is the most important, I think, is that we designed the system for a data scientist. So the system have a very intuitive Python interface. It's with lots of shortcuts, lots of helpers. So the most important for us was to have a entry barrier as low as possible for a person who is good in Python, good in data science, but not exactly who is a rendering specialist. It's also worth to mention that I mentioned that we have support for MDL, but also we have support for Nvidia Substance. So this is a very cool technology which enables to create a recipe for a material and next generate dozillion of similar materials on a rendering time. So we signed a collaboration with Algorithmic a year ago, and we already have substance materials and algorithmics libraries already implemented, integrated with our code. Okay, so let's look at slightly more sophisticated example. So this is a project which we did with a company who is a vendor of capsule endoscopy cameras. And actually, I'm going to show you some results of a pilot which we did with them last summer. So we already completed the pilot test with very good results. And this pilot was organized in a way of competition. So it was about detection of two types of small intestine cancer, and the customer already had a data set of 90,000 of images of these two types of cancer. But they shared with us only 200 images, and they wanted to know if we are able to come close with our results to our results which their data science team obtained on real data. So they wanted to validate our technology and to test if it's useful for other of their projects. So how we approach that problem? We started from creation of 3D geometry, so based on some MRI scans, we created a generative geometry, so we could randomize a shape of intestine, and next we created set of textures to cover that geometry. So this is how the synthetic data set looks like. It's also post-processed by some GAN networks. So what you can see here is a tissue of intestine. So this is a generative material, some floating objects. You can see the geometry. Now you can see how SkyEngine is placing our created models of malignant tissue. So this is a first type of lesion. And the semantic masks is generated automatically for a purpose of semantic segmentation. And here is a model of second type of cancer. So this is kind of polyp. So you can see here that the quality of the images is low resolution image, mainly because this is dedicated for low resolution capsule endoscopy cameras. And for comparison, this is how the real image from such camera look like, and how the system is able to do a semantic segmentation of a lesion on such images. Now let's take a look at the results. So with our synthetic data generation approach, we were able to achieve a recall value on the level of 95% and precision value on the level of 94%. So it was like actually three-class classification problem. So we had two types of cancer and healthy tissue. On the other side, our customer achieved 89% of recall and 87% of precision. And how that happened? Here we can exactly see how powerful the functionality of balancing the dataset is. So once our customer achieved level of precision about 85% on real data, they could only start playing with hyperparameters of model, maybe some data augmentation. However, once we achieved level of 85%, we realized that there are some floating object causing reflections, and also we identified some cases confusing for models, and we just generated more data similar to the most confusing examples. In that case, we were be able to train a model much further and achieve much better results. But we can move further with this topic. So we presented already the data for capsule endoscopy, but we can also generate high quality images for HD standard endoscopy cameras. And here is how the generative materials and renders from SkyEngine look like for standard endoscopy. So here we can see again the synthetic geometry and synthetic images of intestine. You can see the topology and the geometry. So we can use much more information than in conventional way for training, including depth maps, normal maps, which is also pretty useful in some cases. Then you can see how the system can place lesions. So here we can see kind of polyps and other type of cancer. Mhm. We can generate heat maps. We're still looking at synthetic data at this moment, and some intermediate validation phase when the model can detect malignant tissue on synthetic data, so we can make sure that on synthetic data everything is correct. But next, we will see detection of same types of cancer on the real data set. So here we have some real images and model trained in synthetic environment of SkyEngine with inference on real images. Just a few words about our company. So we are a London-based startup. We have also offices in Brussels, Warsaw, and Shanghai. So we grow pretty fast. SkyEngine will be available in a software as a service form after summer this year. However, we already started working with early adopters. So if you would like to test our solution, please contact us. We work on SkyEngine platform with our partners who are actively helping us to improve our solution. And that's all what I wanted to present to you today. So thank you for your attention.